I think we should start. Today is the last session of Professor Park's lectures on differential cohomology theory. And without any further explanation, Professor Park, please, we are listening. Thank you.
Okay, thank you. And I'm very thankful for this opportunity to give these lectures on these topics that I'm interested in. And so today's topic is going to be gerbs with connection, with or without connections. Okay, so let me briefly recall what we did. Um, so basically, we began with uh, this check homology and characteristic classes, right? Then we looked at what characteristic classes are, and we thought about the uh, classification that uh, this line bundles, complex line bundles are classified by. I mean, sorry, the degree two integral cohomology is classified by um, complex line bundles up to isomorphism. Then we ask this question. So what happens if we have connections on line bundles? Then that gives you H hat, or what is known as differential cohomology. And then in the last lecture, we looked into details about what's this H hat. Then this H hat, this differential cohomology, fits into this hexagon diagram, and we saw how this works, how these maps are defined, and why the diagrams are commutative, and etc. So today, if I summarize these, this H2 of M with integral coefficients is classified by line bundles. This this thing line bundles with connection. And question is, what are corresponding geometric objects representing is h n of m with integral coefficients and h hat m, sorry, h hat to the n of m. So the answer is going to be n minus 2 gerbs So this somehow has to do with this probably more interesting question in research, which is that if we think of this iblet to be a functor from space of the category of topological spaces, and up means the opposite category, so that I can just say this is a functor, not necessarily the I mean, I don't have to say contravariant functor by taking up. Then it goes to graded abelian groups, satisfying homotopy invariance. So if I don't even want to say homotopy invariance, then I could just say hotop. So like this. Category of topological spaces. By topological spaces, here I really mean not the really category of topological spaces, but more like the category of CW complexes. Connected CW complexes. Probably I should write it down. So if you learn in undergraduate topology course, then your objects are what, like topological spaces, and morphisms are continuous functions. But for the purpose of algebraic topology, oftentimes you don't really want to work in the category of topological spaces. You really want to work in somewhat better category like this, because so other things like Hawaiian earrings and etc. Like those things create problems. So I should maybe save this. Want to be buried. And it satisfies wedge axiom. So if you have wedge product of a space and you apply it, then you have. Okay, let me write it down. So then it splits into product or direct sum. And the second thing is the mi-arbitrary section. So if this functor E flat satisfies these two properties, then the Brown representability says each En is representable. So, i.e., En is blank is equivalent to pi naught of maps from blank into some classifying space. I mean, some object in your category, like let's say, okay, I'm gonna just write E sub n like this. So then, so if you have is a generalized cohomology theory. I.e., E flat satisfies or Meyer Beatrice, sorry, not biarbitrage. So it's different name. Allenberg, Steenrod axioms, except the dimension axiom. So there are 5 axioms which are called Eilenberg-Steenrod axioms. So if this functor satisfies all these 5 axioms, then this E flat is naturally isomorphic to your singular cohomology that you already know. But then among these things, we sometimes exclude this dimension axiom, but still obtain interesting theory. These are called generalized cohomology theory. Then there is a one correspondence with something which is called omega spectrum. Spectra. So if you have this generalized cohomology theory, then you always get this some sequence of space called omega spectra. I'm not going to go into details because I'm not going to use this at all today. But if you are interested, you could just look up NLab or Wikipedia to learn what it is about. Then if you have the sequence of spaces by taking, this is Brown. And if you have sequence of spaces called omega spectrum, then by taking pi naught of maps of blank and E sub n, then you get a cohomology theory. So really, what I just want to point out here is that this generalized cohomology theory is a rich source for the purpose of topology. So then, so there are at least as many generalized cohomology theories as the number of spectra. So some examples would be like K theory, KU theory, and all variants of them, like KO theory and etc. And Bourdism theories like MU, MO, etc. And something which is called topological modular forms, and elliptic cohomology. These are all versions of generalized cohomology theory, meaning satisfying all Eilenberg-Steenrod axioms except the dimension axiom. And then the question is, given e to the n of x, can we have a geometric cocycle representing each class in this generalized cohomology theory. So one attempt to answer this question was something which is called the Sturz-Teichner program. And what it says is that the field theory with modular concordance supersymmetric field theories degree n over m modulo concordance this must be isomorphic to the generalized cohomology group. So I don't know whether we should call this program right conjecture, because really not much is known about this. I think for Hn of x is clearly known, but then for K theory, not sure. Off the top of my head, I don't remember a reference actually. And and there is a version like if this one being Euclidean field theories, and then it has to do with this differential version of generalized cohomology theory, and much less is known for that direction, I believe. So just wanted to say that the question that I'm just coming back on and on in the series of lectures about this, like what geometric objects representing the cohomology and differential cohomology group classes. So these are actually very deep and interesting question at the forefront of algebraic topology. Okay, so let's go into details. There was like, I mean, this forwards were probably too long. How do gerbs arise? So we consider this sequence of groups. U1 goes to this isometries on Hilbert space, and I mean let me go a little bit more general, like some group G Twiddle, then goes to group G, and then goes to 1. Short exact sequence. So a principal G bundle leads to a a principal G twiddle bundle if and only if the cocycle representing dd of P is trivializable. So let me explain this better. So earlier, in the first lecture, we looked into this. We consider a version of this short exact sequence. Then we looked at this DD being a map from degree 1 check cohomology with this coefficients in values in PUH that goes into this check cocycles valued in S1 in degree 2. And this is just coming from the sequence of C in R mod C 1 1. So the induced sequence from this gives this iso. So then an element in here was an isomorphism class of principal PUH bundle that corresponds to degree 3 integral cohomology class, which is DD. But I said that, but I didn't give you a construction of it. So the proposition that I'm trying to explain now has to do with this construction. So let's do the following. So on M, this is a smooth manifold. Choose a good cover U on M. Recall that a good cover is an open cover of M that all open sets are contractible, or triple intersection, double intersection, triple intersections, and so on. All intersections are contractible. So that's a good cover. And on a smooth manifold, a good cover always exists. Then, if we have a principal G bundle, what does that mean? So then on each double intersection, UI intersection UJ, in my notation UIJ. So there are transition maps G sub IJ valued in the group G. So principal G bundle or principal PUH bundle in the previous example. So we have this transition map on double intersection. Then so this is a part of this sequence. So we have this projection map, and then note that this is contractible. So there must be homotopy from this to a constant map. That those two should be homotopic. Okay. So then note that this U1 goes to G twiddle, goes to G. This is a vibration. And what is a vibration? It is a continuous map such that it satisfies the homotopy lifting property. So this is a vibration. So, and because this is being contractible, there's a homotopy in this level. So that homotopy lifts, right? And then this Gij would lift to G, sorry, Gij toidal, then I want to believe the property. So it satisfies commutability property. So we have G twiddle ij dot G twiddle jk, G twiddle ki. So if I did the same thing with G, then because this is a cocycle for the differential map for principal G bundle, so it's going to satisfy 1, but here it's not 1. However, we know that this must be lambda ijk on triple overlap dot 1 of G twiddle, and where lambda ijk is degree 2 check cochain valued in U1. Then it's a simple exercise to show that lambda is a degree 2 cocycle. So I said this is cochain, but it actually satisfies this delta lambda 0 on ijkl. Second, this check homology class lambda does not depend on the choice of lifting, because HLP doesn't say that this lifting is unique. So you might take different lifting, but it doesn't matter. So that means this cohomology class is precisely the obstruction for this principal G bundle to lift to principal G twiddle bundle. So we get this this lives in degree 2 check class. Because M is a good cover, this being U or M doesn't matter. They're isomorphic. And this is isomorphic 2, degree 3 integral cohomology. And we define this to be DD of P. Okay. And this is an obstruction of the existence of lifting. Okay. So then we are done. So this lambda ijk is very closely related to what a gerv is. There are various versions of gervs, like this using a check cocycle, as I alluded you here, or there are more like historical or algebra geometric version, like looking at gerbs as a stack, like it's a sheaf of groupoid. So when you say a sheaf, oftentimes we consider the sheaf this thing valued in sets, but then now you have to consider the situation that it is valued in a groupoid, right? Then that requires an extra care, and those are called stacks. So if you are interested in those things, like really the sheaf of groupoid language, then you might want to look into this book by Bulilinski. But today, what I'm going to specialize about gerbs is this thing called burnt gerb. So let me just go ahead and explain what it is, and then say more. So let y to m be surjective submersion. So surjective, like this projection map, like it's okay. Oftentimes we expect it, but then why submersion? I'm going to explain. So, this fiber product, if you have this map, then the fiber product with itself, is what is often we denote like this, and then for the convenience, I'm gonna just write like y to the bracket 2. And what is this? This is collection of y1, y2 in y cross y, such that pi y1 should be the same as pi y2. So this is a fiber product. And is this a manifold? If you take a fiber product of two smooth maps, like in general, if you have like m, let's say it's n1, n2, then map goes in this way, f, g. And if you take fiber product, is this a manifold? In general, no. But it is a manifold. In this case, pi is a submersion. So that's why we care about this map being a surjective submersion, because we want to remain in the category of smooth manifold. Then some notation. This y to the bracket p would just mean p-fold fiber product, like y1 yp that lives in y to the p, such that pi y1 equals to pi yp. Then I'm going to also use this notation like pi of i1 I of k. What does this mean? So it goes from p-fold fiber product, and that goes to k-fold fiber product if p is bigger than k, right? So then I should tell this is like p copies of y, right? And I'm gonna take like I ones, I tooth, and then so this means on which copy that we project onto, right? So if I have y1 comma dot, 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 y sub p, then it goes to yi1 comma dot, 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 yik. So yeah, and here comes what bundle gerb is. So this is due to Murray. A bundle gerb is a triple L, pi, and mu. It's not difficult. Where this pi is y to m, a surjective submersion. Then second, this L is a principal S1 bundle. Like you could say U1 bundle, or you could also say complex line bundle, depending on what your context is. Or you could also say C star bundle. I mean, yeah, the complex numbers minus 0. So over the two-fold fiber product, we have this S1 bundle. Then that has to satisfy this thing. So first, this mu has to exist, and the mu is pi 1, 2 pullback L. So pi 1, 2 is defined on 3, 4, 5 product and projecting the first and second copy. Then using that projection map, we pull back L. Then tensor pi 2, 3 pull back L. That goes to pi 1, 3 pull back L. This is an S1 bundle isomorphism. Then for mu has to be associative over the quadruple fiber product. So if you have this quadruple fiber product, then you have 4 copies, right? And then you first take, you take parentheses among 2, and then you apply the multiplication map, and then do another multiplication map, and then you take different parentheses, and then doing the same, then they should agree. So that's the condition. So this might sound like quite abstract, but so let's define this y sub u as follows. Like it is consisting of pairs x, comma I. Here, x is in M, the base manifold, and I is coming from the lambda. Lambda is the index set of U, the open cover U. Like UI, UJ, like these IJs are these indices, right? On this open sets in the open cover. And then the condition is that X lies in U sub I. So this is subset of M cross lambda. So then this thing, so this pretty much, slightly different, but it looks like an open cover. if we take pi like this is a surjective submersion. But this is indeed like open cover. So if you think about what it means by 2-4 fiber product or 3-4 fiber product of this thing. So a use of surjective submersion here, of course, is for remaining inside the carrier of smooth manifold, our construction, whatever that is. That's one purpose. But the second purpose is that this is a generalization of use of open set. Like this thing means just an open cover, and over double intersection, you have a line bundle. And then this would mean like if you have like fiber in this like U1 intersection U2, then you have another fiber U2 intersection U3, and then over triple overlap, then you have this fiber U1 intersection U3, and then if you tensor two fiber, then there is this ISO, and then over the quadruple overlap, you satisfy. You require it to satisfy the associative condition. So that's bundle germ. Well, you might think of it a little bit complicated if you're new to this. However, like compared to the shift of groupoid definition, this is drastically simple, and like you don't have to worry about technicalities of having to deal with stacks. So these are like really pretty straightforward objects and morphisms, the category of smooth manifolds, and like quite typical constructions like S1 bundle. So for these reasons, if you look at literature dealing with gerbs and developing theories, most people either they use this check co-cycle version or they use this bundle gerb. Probably, I believe these bundle gerbs are more widely used. And if I tell you just brief history, I heard of this from David Roberts in Australia. He said, he wrote papers and interacted with Murray. And then when Murray first developed this thing, there was like early in 1990s. Then he ordered, in those days, now you go to some internet website and then you buy books. But in those days, you fill out some catalog you look into catalog and then you fill out some postcard and then you order it by mail, and you have to wait until the book comes to your office for a long time. And then he looked at the explanation, this a brief summary of Brzezinski's book, and then before the book arrives, he based on this description, this person Murray thought about what it has to be, and then he wanted to compare. He invented bundle gerb while reading this explanation in the catalog, and then he wanted to compare, and then he was quite surprised that the thing that he invented is, looks drastically different from what's in Brzezinski's book. So there was some behind story about the invention of this thing. Okay, now, so let me give you a construction of DD let me write this curly L. Dixie-Miller class. So how I do that? Let L be this line bundle line bundle, projection, I mean the surjective submersion, and bundle job multiplication, or sometimes we call bundle job structure because it basically characterizes what the bundle job is. This is a gerb, so I'm going to denote this category of bundle gerb like gerb M. So I'm going to tell you more about this category later, but for now, let me just say that this is an object in this category, and then choose an open cover U on M, then consisting of UIs. We may take local sections like sigma I is defined on UI goes to Y. Because this pi means Y goes to M. This is surjective submersion, and we take local sections. Then you can also take this local section over double overlap, sigma I, sigma J, defined on Uij, and that goes to this two-fold fiber product. So this is clear that this is well defined. So if you take X, then it goes to sigma IX, comma sigma JX, and then if you project this thing to M, that goes to say X. So I mean how this map is defined is obvious. So then consider this diagram Uij that goes to this two-fold fiber product Y, and then there's line bundle ellipse double. This two-fold fiber product, and then you may this is sigma I, sigma J. And then you may pull back bundle using this sigma I, sigma J, this map, and then pull back this line bundle L or S1 bundle. Then taking a section Sij, or alternatively, you can think of having a map Sij directly going to L and making this triangle to commute. Either ways. So then, on this triple overlap, we can think of Sij of X, then Sjk of X. Then what this bundle job structure mu does is that if you tensor this thing, then it goes to Sik of X, but here you have something Ijk X. So over triple overlap, you obtain this function. So S1 valued function. So then it is not difficult to show this. This is an exercise. Show that the associativity of mu implies that lambda ijk, this is a check cochain, is a degree 2 check cocycle on U. And second, if you check homology class, this lambda, that does not depend on the choices made. So here, definitely you need some choices that you have to make when you're taking this local section. And I mean, you might take a different one. But then if you look at this check homology, it's independent of your choices that you make. So then we may define this DD of L, so Dixmuir duality class of L, to be this degree 2 check cocycle valued in S1, i.e. this is degree 3 integral cohomology class. So now let me go to this curvatures and connections on gerbs. So only background that you need is to know about what is a connection on a principal G bundle and what is a curvature of a principal G bundle, and curvature of connection on your principal G bundle. And I could tell you about those things, but because I might not have enough time, so I'm gonna just leave it to you to look up. And I believe it won't matter too much to follow what I'm going to explain now. So a connection on L, this is bundle gerb L pi mu, is a connection nabla on L. So this bundle gerb has this S1 bundle part. Then a bundle gerb connection is a connection on this line bundle over double overlap, right? Like double overlap or this 2-fold fiber product. The connection on this thing, right? But you would like to require that this connection is compatible with mu. So what does that mean? So this pi 1, 2 pullback L. So this is the bundle gerb structure mu, right? Pi 2, 3 pullback L. Then there's this map mu and pi 1, 3. This must be S1 bundle iso, right? Line bundle iso. And if you have this connection, so originally mu was S1 bundle iso, but you want to require preserving connection. So it must be connection preserving isomorphism that you will not require as a definition. And for the case of line bundle, you have just connection, and then you talk about curvature. But for the case of gerbs, there is another thing called a curving. So curving B of L, this is L pi mu, with connection nabla, is a differential two-form on y such that this curvature of connection. Curvature of connection is two form, right? On this base manifold 2-4 fiber product. Then this B is lives on Y, right? And then you pull back using pi 1 pullback and pi 2 pullback. Like this is projecting this to first copy to second copy. So your pi 2 pullback minus pi 1 pullback B, B. And that should be satisfied. So that's a curving. So a bundle jerk connection bundle jerk with connection would mean this L, I'm going to denote it by L hat because I've been denoting differential stuff with hat. So topological data, L, pi, mu. This is bundle jerk. And then connection and curving. So this is a bundle jerk with connection. Then I'm going to denote the category, jerk, blah, blah, M. So sometimes people call this connection with connection and curving as connective data, the connective structure of this bundle jerk. But people often use bundle jerk with connection. So I'm going to just say that. Then this connection and curvature, I mean, this curving, this is not actually something that corresponds to a curvature. For example, if you consider line bundle, if you take line bundle curvature, that's actually your Weir-Chun form. Basically, if you take the first Chun class, which is degree 2 integral class, and if you tensor with R, then if you have this curvature form and you take real cohomology class and drum class, then they should agree with the thing that you obtain by tensoring R from the integral class. But this curving doesn't do that job. So you have to actually introduce some new concept, which is called the sweet curvature. But for that, you need a little bit of prep. The following sequence is a long exact sequence. So what is a sequence? Is this 0 that goes to differential form zone M, like K, degree K, let's say. And then this is the surjective submersion pullback. So degree K, differential form zone Y. And then this delta, I'm going to define. And it gives you K forms on this 2-4 fiber product, and so on. Where this delta is basically alternating sum. K goes from 1 to P, minus 1 to K minus 1. So the sign starts from plus, and then pi I1 dot 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 I sub K dot 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 I sub P, and then you omit the case 1, and then pull back. So basically, it has to do with this. This would be like this delta map, right? I mean, if you see this pi 2 pullback means like 1, 2, and then you omit 1, right? And then pi 2 pullback you have. And 1, 2, and then you omit 2. So you have pi 1 pullback, and then the sign is minus here. And you go in this way and the final. So then, actually, so if you are actually curious about the proof, see Marie's paper. And a version of this, if your surjective submersion is open cover, then button 2 in chapter 2 or something, it has it. It was somewhere around like 80 something pages or 90 something pages. I forgot. And why do I say this? To talk about three curvature. So you note that curvature form of a line bundle connection, like from your bundle curve, connection on your bundle curve. And then you take D, then there must be 0, right? Whereas this curvature should satisfy this delta B, right? But then this D and delta commutes. So, i.e., this dB, sorry, delta B no. I should say in this way. So it's a little bit confusing, but like, where does this dB lives? dB lives actually here, right? And then, so this equation actually holds in here. So then, because this is a long exact sequence, there exists a unique H, which is degree 3 form on M, closed form, such that you pull back with surjective submersion, that should be the same as dB. So this is the, if we let L hat L pi mu nabla B is a gerb with connection on M. The 3 curvature of L hat is H. So sometimes people call it H, 3-form flux or something. It's known as 3-form flux. In string theory, people also call H flux. Then, just as if you take the first term class and tensoring R gives you the Dirac class of your curvature form, we have the theorem that for this L hat, if you take DD class of your bundle curve, and then you take, if you realify it, so this R map is the thing that we considered before, that if you have integral class and there's a mapping to real cohomology class. So that thing, that should be the same as this, the drum cohomology class, or H. Okay, so now let me give you an example. this is called the elliptic bundle job. So this is pretty similar to what we considered earlier about how these gerbs arise. So basically, you begin with this pi map y to m. This is a principal, let's say, PUH bundle. It could be just group G. Then there exists a natural map from this 2,4 fiber product into PUH, and let's say this map G. So what is this map? So this is the 2,4 fiber product of the total space of principal G bundle. So if you have the same fiber, and if you take two elements from the same fiber, because of the transitivity of the right action of this group, there should be some group element associated to those pair of elements. So if you have y1, y2, then there should be some group element that you take, and you obtain y1, y2 in here. So pull back this UH on the top of PUH to obtain. So basically, some L, which is obtained as pullback of this U1 vibration here. So then, so we have this L for bundle germ, and then pi, the surjective submersion, and then we just have to know this mu. But actually, it's not difficult. That mu is defined by the right coset multiplication. Why? Because if you look at the fiber, then fiber is always the U1 right coset. So for example, a fiber, if you take an element here, like G1, like G of Y1, Y2, then a fiber here is going to be U1 is right coset. So I'm going to say like this, G, Y1, Y2. So this fiber. So these fibers, you can do this right coset multiplication, and that gives you the bundle germ structure. So I'm going to just explain some brief thing and then stop. So there is this thing called the link complex. So if you read this book by Bott and Tu, then you have seen this. So what is it? I want to draw this diagram that you begin with check degree 0, then on open cover, then the group U1. Then you take check differential delta, then you go check degree 1, then or open cover and values in U1. Then so on. Check 2, U1. Then you have check degree 0 on open cover, but then over each open set you have one form. So these are like U1 valued functions, but here is one form. Then similarly, two form. And so on. And then you take D here. Here you should be a little bit careful because it's from U1 valued functions. You don't take just D, but you have to take D log. Just a little bit of technicality here. Actually, what makes the link complex a little bit special. D log. Then you have check degree 1 on open cover and with one form. Then D, and then you have check degree 1 and 2 form. Then take D and so on. D log, check degree 2, then open cover, then D, check degree 2, then U, D2 form. Then here you have check differential vertically. So this double complex is called link complex. And so this is total degree is 0. So if you consider the form degree and function degree, and if the sum of the degree is 1, and sum of degree here is 2. So you consider this total complex with this total differential D. So is consisting of this check differential and then D, but you need actually some sign here, -1, then form degree. So then this total complex with this D, you take cohomology. And that is the link cohomology. Actually, I should say on open cover U. Then why am I going into this link cohomology? First proposition is that if you have L hat, which is jerk with connection on M, it determines a link 2 cocycle. So if you have a jerk with connection, then it defines the link cocycle. How? You take, so lambda ijk, we have seen how you take it. So for this one form, so it's degree 2. So I should have like check degree 2, degree 2 check cochain, and over double intersection, I should have one form, and over an open set, I have 2 form. So over double intersection, I have one form, and I should have one form, and then over open set, I should have 2 form. And how do I get that? So you just pull back Sij that we considered before when we are talking about the DD class. Then you just pull back the connection. And then this thing, you pull back with the local section. So then you get this local forms. So then you have, and it's an exercise. Show that it satisfies. If I write this lambda hat, this total differential applied to lambda hat is 0. And then when you're taking these things, you have choices involved, independent of choice. And then second proposition is that L1 hat and L2 hat are isomorphic. Caution, I didn't explain yet what this means, but if you just take it for granted that you have some notion of isomorphism, then two gerbs with connections are isomorphic. They have the same Kleene cohomology class. So each define Kleene degree 2 cocycle and their cohomologues. And then there's this theorem. Actually, this is not an obvious theorem, but this is a fact that this Kleene cohomology of degree P of M is isomorphic to the differential character, differential cohomology we considered last time, degree P plus 1. So if this P is 2, then this isomorphic to degree 3 differential cohomology class. So what does this say? Pi naught of this gerb with connection over M. Pi naught means isomorphism classes is isomorphic to S groups. Degree 3 differential cohomology class. So it gives you a classification that up to isomorphism, degree 3 differential cohomology classes are classified by gerbs with connection. And from this, you can also expect that what happens if you consider degree 3 Kleene cocycle. So then that is going to represent, that is going to be a check data for two gerbs, right? Two gerb, not gerb, two gerb. And if you go to degree 4 Kleene cocycle, that's going to be 3 gerb, and so on. Then two gerbs would be isomorphic. Two isomorphic classes. This Kleene cohomology classes of two gerbs would be a degree 4 differential cohomology, and 3 gerb would be degree 5, and so on. So let me finish with just this one remark. This about one thing that I just blackboxed. So what should be an isomorphism between between two bundle gerb? So you might wonder, well, isn't that easy? So if you have some gerb data, then if you have this line bundle, should that be just line bundle and this surjective submersion like Y over M? So then it should be like some sort of like commutative diagram Y prime, and this must be diffeomorphic. So that's some sort of naive way to imagine what it is, but no, that is not true. So that is not the right way to define an isomorphism between two bundle gerbs. If you define naively, like L isomorphic to L prime and Y prime over M, this are differential and this commutes. Then what happens is that this L and DDL and DDL prime are same, but L prime, which are not iso. So this this notion of isomorphism is not a good notion. So we need something which is called the stable isomorphism of bundle gerbs. So this is the correct notion. And if you look into Waldorf's, Conrad Waldorf's more morphisms of bundle gerbs. So then he sort of generalized this notion of stable isomorphism. But I think for us, for especially for beginners, this paper is probably the most readable one that sort of subsumes the notion of stable isomorphism initially invented by Michael Murray and Dennis Stevenson, and at the same time, it gives you some sort of an easy grasp of like one morphism, like the stable isomorphism, and two morphism between. I mean, the morphism between two stable isomorphisms. So it gives rise to this gerb with connection of M. This is actually two groupoid. So you have objects as gerbs, and one morphism as a stable isomorphism, and two morphism as the morphism between two stable isomorphisms. Okay, so that's all I prepared for today. Thank you.
Thank you so much, Biangdo, for the very
Thank
nice
you.
and hard talk. If there are any questions, please don't hesitate to ask. So meanwhile, I have one question, Biangdo. You mentioned two gerb. What did you mean by two gerb and three gerb?
So so one gerb is just gerb.
U1, yeah.
Yeah, no, just one, just number one.
Okay.
Because there's this the usual gerb, like the historical one, but then people found like there are higher analog of gerbs, right? Like zero gerb would be the line bundles. Then you might ask, what is the higher analog? Like, what is a two gerb? Right? That's your question, right? What should
Yes.
that be? So then, if you, I think it's going to be easier to just explain using the lean complex, right? So if I look into this, if you have, let's say, Gij, right, the transition maps, or I mean, it's a U1 valued function, but defined on double overlap. That's a transition function, right? And then, you know, this connection form defined on each open set, right? So then, only using this data, this local data, actually you have a this U1 bundle with connection. And then we just have seen that for bundle gerbs, like one gerb, you have lambda ijk, and here you have aij, and you have bi. This data gives you just use your gerb with connection. So what is a true gerb? Topologically, then it should be lambda ijkl. The check data should be, or quadruple overlap, you have a function, U1 valued function. And then you have on triple overlap, you should have like aijk, like this must be one form. Then double overlap, you should have bij, two form. And each overset, you have ci, three form. So that local data is like two gerb with connection. And then higher gerb, it has one more entry and one more entry and so on. So does that help?
Yes, thank you. So, why do we always can we replace U1 by some other group? Like we can do direct sum of U1s, right? But that's kind of trivial. But maybe because U1 is
For this group.
yeah.
So that's actually a great question. But I should say um, I have almost zero expertise about that direction. Uh, yeah, sorry about that. But that's
Um,
because so that has to do with different. So I said like U1 bandit or circle bandit gerbs, but you might ask like, what if you have different group, right? That's your question, and especially what if we use a non-abelian group, for example. So so people have been like working on those topics like in late 2000 and probably early 2010, like around the time that we were in grad school. People worked on it, and actually Shane Glass, this guy is actually an expert about
right, right. Yeah, I
that topic.
remember
Yeah,
he was talking. Yeah.
yeah.
Okay. So I think that there is no more questions, but I mean, I can ask more questions, but I don't want to
You can
hold you
ask
up
me.
for too long. So is like can we always find the curving? Like is like or
So
sometimes
you're talking about the existence of connection. So I didn't go into today, but yes, that's a good question. Basically, the technique requires you're using partitions of unity to glue things. Yeah,
no,
so
but
that
the
appears in more.
curving is more
Yeah, carving as well. Yeah.
oh okay,
So
it uses the
yeah,
same technique. Okay.
yeah. So there's a question. Let me see.
Yeah. Is there a question?
Wait.
Yes, there is one
Kajra
more.
has this question. Yeah. Can you give a hint for the proof the last theorem? The last theorem would mean this one. Um, ah, you know, because there are too many ways, but probably the most closest one to the intent of this question would be like the original proof that people came up with. Like Chigor Simons defined this, and Deligne defined this, and then there should be some first one who showed this. I think if you look into Brzezinski's book, so what's the title? It's like loop spaces and geometry quantization and something. Characteristic classes. So anyways, I'm going to put up the notes for today's lecture on my webpage, the tech version as well. And then in there, you'll be able to find this reference. And then if you look into this book, he doesn't prove it. He basically refers um, some other paper. It's by Ellen Esser. Uh, um, the characteristic classes of flat bundles or something. So basically, um, I think that's the contents of the paper is going to be answer to your question. But uh, the the reason that I said that there are many ways to answer this is that, like for example, if you can view this along the vein of the discussion last time. So we discussed this uniqueness theorem. Uh, where was it? Like Simon Sullivan proved that what fits into the middle of the hexagon diagram is determined uniquely, and actually the Deligne thing fits uniquely in the middle, and perhaps some better explanation, some more intuitive and tangible explanation could be like here if you want to consider, let's say for degree 3, and then higher degree is almost like similar. Right? So say degree 2 and degree 3 here. So then here you have check data lambda ijk, and you one from aij, and then you have bi. Then here, like you have some like integral degree 3 cochain, degree 3 integral chain, and then you have some homotopy 1 degree less, and then you have degree C form. Then establishing correspondence between them. So this looks degree 2, but actually this is actually the same as having an integral chain. So basically, like for this one component, you know that they are the same. You just have to do a little bit of diagram chasing to figure out how this thing in the link complex actually corresponds to this co-cycle data for this of this differential cohomology. Then it's going to answer to your question. But you might not know this kind of triple model. So actually, this this model is due to Hopkins-Singer. This seminar paper, if you look at section 3, then you'll be able to find this triple model. Then that model and comparing with that is going to be not that difficult. And then if you want to prove it more generally, then you're just having one more entry. So it's like one more layer of diagram chasing, things like that. That answer your question? Okay.
Okay, so hey, how you doing?
Good, good.
Yeah, this was the last lecture was the hardest. You saved all the hard stuff for the last one. Is there any other question for Professor Park? Okay. So let me, on behalf of everybody here, thank Professor Park again for taking so much time out of his busy schedule
My
to
pleasure.
give these nice and awesome lectures.
Here's a great question. So what do you recommend for the reading? Actually, the purpose of this actually, I'm really grateful for this opportunity to actually give you some intro about these things. And the purpose was giving you some ideas about like several possible directions of research in this area, especially like things. If you're more interested in general aspects of differential cohomology theory, then there's things from the section, I mean, this second lecture is going to be more relevant. But if you're more curious about like this higher differential geometry objects like jerks, then like what we discussed today are more relevant. But I mean, and at the same time, like I kind of felt some necessity, like if you want to know about this area and if you have to read the whole Brzezinski's book, then well, that's gonna take 1 year or something. It's like too much for graduate students. So I just wanted to kind of compactify within like 3 hours. So yeah. So to answer the question. It depends on your interest, like what you want to specialize and to look into more. But based on this kind of background, then I think you can just pick some direction and try to read the paper. I mean, for students, the most difficult thing is like the gap between the textbook and then the paper. Then I guess knowing this much at least gives you some. I mean, not everything, but for some things, like you'll be just directly go to the paper. So yeah, so I would answer like um, so this papers of your that fits to your interest, and I'm gonna I mean in the text version that I upload on my webpage, there are some references. Then mm, you can browse those things to see if this is relevant. And also, you can ask privately by emailing me or something, and then ask my opinion about your background is this much, and if you want to hear about my opinion about what about reading this paper and what's the prospect of doing any further research from studying from this paper, then I'd be happy to answer that question. Okay, thank you.
Thank you, Bengo, for the nice answer.
Thank you, Sajid.
Okay, so hopefully we're gonna have you here in the near future. Have you in Iran?
That'd be
And,
great. Yeah.
the student that asked you the question, he's very interested in like he really likes reading advanced books, and he's a second year student, but he's like
Oh,
very
cool.
yeah, driven. So
Okay.
nice.
That's actually, yeah, that's actually a correct use of Korean. Thank you.
Yeah, he probably used the Google Translate.
Yeah, not
I
less.
should have
Yeah.
done the
Maybe
same.
like if people are interested, like not next week or like next month, but sometime in the near future, like sometime around next year or something, I'd be happy to give some other lecture series about other topics in this area
Sure,
if you're
sure.
interested.
Yes, yes.
And also, if you don't have speakers, uh, then I'd be
Yeah,
happy
we
to
always, I
volunteer.
mean, yeah. No, I mean, like
I
we
mean, yeah.
always have you in or I'll try to have you give a lecture again. So
Thank you. Yeah.
yeah, so I mean, now I have to go read some papers and see what these things really are. But yeah, it was very nice. Thank you so much.
Thank you. Yeah.
Okay, so if there is more questions, or I think there is no more questions from the students. Um, okay, so I'll thank you again, Yangdo,
My pleasure.
and
Thank you.
we're gonna have you again on this series and to give a talk.
Yeah. Yeah.
I think you
Thanks.
were the
Yeah.
most dedicated speaker yet for so
Great.
yeah, we'll definitely have you again. Thank you so much. So I think I'll see you in near future. I
Yeah,
keep
yeah,
in
we keep in
touch.
touch.
Yeah,
Sure.
definitely.
Yeah.
Okay. So I'm gonna say goodbye and have a good
Okay.
night.
Yeah. Thank you. And
Yeah, say hi to everybody. Okay.
sure, I
Have a
do
good
that.
night.
Okay.
Bye.
Yeah.
Bye,
Bye
everybody.
bye. Thank you.
Bye.
Thank you, everybody.